All right, everybody, we're back. We're on page 276, and we're still basically doing limits at infinity, but the question itself has changed, right? So the question here says, find the horizontal asymptotes. Now you need to know that the horizontal asymptotes represent the limits at infinity and negative infinity. Do they represent them? No. They're how you find them, I guess. No, it's the reverse. The limits are how you find the asymptotes. So let's just do the problem. So I'm going to need, it's not a rational function, right? Not a polynomial or a polynomial. So I'm going to need to go in both directions. I'm going to go to positive infinity, go to negative infinity, see what we get. So let's do that. So we're going to go limit as x approaches infinity of, should I just factor to begin with? I mean, I feel like I should. It would like save me a little bit of time. So I'm going to do that. I'm going to say it's the absolute value of x, square root of, we got 6 over x squared, we got 7 over x, and then plus 8, and then all over x minus 3. So now I'm going to do the thing, I'm going to positive infinity. So at positive infinity, we can replace the absolute value of x with just x, right? If we're going to negative infinity, we'll replace it with the opposite of x, or negative x. So let's do that. So this is the big moment where you make this substitution. If you don't navigate that correctly, things aren't going to go well. So we have 6 over x squared plus 7 over x plus 8. And we know that the only thing that really matters in there is going to be the 8, because when we go to infinity, 6 over x squared, 0. 7 over x, 0. The only thing that really matters is 8, but you got to write them anyway. All over x minus 3. So far, so good. All right, now we're at the point where we're going to divide through by the highest power of x in the denominator, always in the denominator. Limit as x approaches infinity. Okay, so in the numerator this time, we have a product, right? So I can divide, it's like a times b divided by a is either a over a times b or a times b over a. Why would you ever choose to do b over a in that scenario? I don't really know. But I'm going to do x divided by x is 1, so I just end up with this radical. 6, oh gosh, too big. 6 over x squared plus 7 over x plus 8 over 1 minus 3 over x. All right, I see a lot of zeros here, right? Because I'm taking the limit to infinity. So I actually am just going to end up with the square root of 8. All right, so, but the problem is to find the horizontal asymptote. So I'm going to say, therefore, y equals radical 8 is horizontal asymptote. Okay, now we're going to go back and do negative infinity. So let's do that. The work is like substantially, man, I'm just scrolling all over, is substantially the same. Limit as x approaches negative infinity, absolute value of x. Really glad I get to write this over and over. This is the first time ever that I've filled in the notes. Like when I write the problems, I just kind of like think, does the problem work? And if it works, I put it in the notes. I have never done this before. I'm doing every problem in the notes. It's pretty crazy. You guys do a lot of work. And to get a good set of notes, whew, I don't know, like tons of work. Because my handwriting's terrible. I'm not writing myself little reminders everywhere, which I assume you are or you should be. Like I'm straight up doing the problems and I'm talking through the things, but like not taking great notes. Like these are the bare minimum notes. What ends up on my screen. If you combine it with what I'm saying and those sorts of things, then you get some good notes. All right, we're going to negative infinity, which means at this step we replace absolute value of x with the opposite of x, so with negative x. I used to always just say negative x, and then I taught Algebra 1 at some point. Let me write while I talk. And when I was teaching Algebra 1, people found it very confusing when I would say like negative x. Because like negative x, I don't know why that's confusing, but people prefer the opposite of x. So now I say that all the time. That's what happens when you become a teacher. You like change some of the things you do. I used to be so much faster at doing problems. Now I like can't not explain. And so like, you know, it just takes longer, which is fine. It's not a race. All right, we're gonna do this. So basically the same work here. Divide through by x. I get negative. Almost forgot. Remember the last time when I almost forgot that? It was bad. I hope you remember. Hope you were watching. You know, like and subscribe. Except these are not public; they're unlisted. So I mean, still, like and subscribe. There's a lot of videos there that could help, but you're not really doing the channel any favors if you like this video. On the other hand, like putting in the work, wouldn't mind a thumbs up every once in a while. All right, the whole point is to find horizontal asymptotes. And there we go. All right, should we look at this one on the calculator? I feel like we should. So I'm going to share a calculator page, calculator screen with you so that you can see what we're doing, right? So I'll do two things. I'll let the calculator find the limit just to confirm that we can still do it. See some calculus still up here. I'm in a new document, I think. Calculator. All right, I'm going to define the function f of x. So we'll take the limit, just review, like, where's the template? Square root. I always type square root, but you should be using the template. It's faster. Almost everything is faster using templates on the handheld. All right, we get this. All right, so I want the limit. Limit is x approaches infinity. You just hit the pi key a couple times. F of x, 2 root 2, because the calculator is obsessed with simplifying radicals. It will always rationalize. It will always simplify. You cannot convince it otherwise. If I want to go to negative infinity, the simplest thing to do, arrow up, paste down, and fill in the minus. There we go, negative 2 root 2, which is negative root 8. Let's look at it on a graph, because that's like, right, we're saying these are the horizontal asymptotes. So here we go. I'm going to graph f of x. You can press the var key and find that. One of the advantages of the var key is when you choose a function, it puts in the parentheses for you, which saves you like no time, but still like do it a billion times, it'll save you some time. All right, so I'm going to put in square root of 8, and I'm going to put in negative square root of 8. And then I'll zoom out so that we can see, right? Because these are behaviors at infinity. We don't really care what happens locally. For example, right there, this function is intersecting its horizontal asymptote. Sometimes people are like, oh, I thought it could never reach it. I thought it could never get there. It can intersect it an infinite number of times. The real issue is that as you go to infinity or negative infinity, it approaches that value. Doesn't mean it doesn't ever hit it. It could be above it, then below, then above, then below. Sine of x over x does that. That's a good one to look at, which we have looked at before, so maybe you remember that. What am I doing? Zooming. What am I doing? Don't press up. Pressing dock, look at me. Zoom out. And then, I don't know, look at it. See? Woo, definitely. Let me trace. Menu 5, enter. I'm going to trace to the left. And you can see we're definitely approaching this line. Like, look at that. Decimal's not changing anymore. 2.7 has locked in. And it's just going to stay the same forever. So like we could keep doing this, but you know, let's get back to the notes. Let's do one more in this video, and then we'll cut it, come back, we'll do the rest, and we'll keep going. We're on a roll. Classic dad joke, right? Like, I'm on a bagel. Haha. All right, so find the horizontal asymptotes of this. This is a weird function. It's a piecewise function. So we really have to pay attention to like which branch is doing what so that we can figure out like what's happening overall. Also, it looks like I'm gonna have to use a theorem here that I've not yet explained, but that's okay. All right, so if x is gonna go to negative infinity, let's look at our definitions. We got this weird rational function when x is less than negative 3, which feels like negative infinity is less than negative 3. So let's start there. So we always start with the notation, limit as x approaches negative infinity of g of x is equal to. So you want to start with that because you're telling people like, what am I doing? The limit as x approaches negative infinity of the rational function, which is x squared plus x plus 2x, 2x minus 3, struggling, 3 minus 4x squared. Oh, now there's a keyboard up. I wish you could see this. Get out of there. 3 minus 4x squared. Okay. This is a rational function. I know for rational functions, what I want to do is divide through by the highest power of x in the denominator. So I'm going to do that. Limit as x approaches negative infinity. So x squared. Divide every single thing that I see by that. So I'm going to get 1 plus 2 over x minus 3 over x squared over 3 over x squared minus 4. All right, part of the reason we do that is that a constant divided by x to any positive power, so x to the 0.01, that would work. X to the 3000 would work really fast. A constant divided by x to a power is going to go to 0. So this is going to give us negative 1/4. Therefore, y equals negative 1/4 is a horizontal asymptote. It's really NHA or a horizontal asymptote. I don't know. I go back and forth on it. I've discussed it probably several times at this point in videos. One of the benefits of this is that you get to hear the same stories that I tell over and over again, because I can't remember if I told them, when I told them. I would say who I told them to, but like you're the only ones watching this, so definitely told them to you. All right, if x is going to be greater, if x is going to infinity, I should say, then x is definitely bigger than negative 3. So that's the branch we're going to use. This one's going to be a little weird though. So let's do this. We got the limit as x approaches infinity of g of x is the limit as x approaches infinity of replace, right? So it's going to be, I'm going to go with the quantity here for some reason, sine of x plus x over x squared. All right, what's happening? So I'm going to break it up because, you know, why not? Get sine of x over x squared plus limit as x approaches infinity of x over x squared is just 1 over x. And one of these I know, right? I actually basically know both of them, but one of them I know for sure is 0, right? The second one is definitely 0. So this is definitely going to be 0 right here. The issue is sine of x over x squared is like a little more complicated because like what is happening, right? So here's how we're going to think about that. So, and this is going to be, it's called the squeeze theorem. We're going to squeeze this limit between two other limits that we definitely know. So watch and learn, everybody. All right, so I know that sine is in between -1 and 1 because that's the range of sine. X squared is positive. Also, we're going to infinity, so x is definitely positive. So I know that this is also true. -1 over x squared is less than or equal to sine of x over x squared less than or equal to 1 over x squared, right? Divide through by a positive, you don't change the signs. All you do is divide through by a positive. We get this. We're so close. If this is true, then the following must be true. The limit as x approaches infinity of -1 over x squared is less than or equal to the limit as x approaches infinity of sine of x over x squared, which is less than or equal to, going a long way here, the limit as x approaches infinity of 1 over x squared, right? These situations are usually very contrived. Like it's usually very easy to decide like what should be on the left-hand side, what should be on the right-hand side. Like in this case, it was very clear to use -1 over x squared, 1 over x squared. Usually you don't have to worry about that. Like it is a thing that just kind of makes sense. But now look at our limits, right? We have two limits that are definitely 0. 0 is less than or equal to this, like probably 0. Like you probably felt like this was 0. Sine is like very small and x squared is huge. But this is how we rigorously show it. And then this is less than or equal to 0. Therefore, we know that the limit, like how could it be, if it's between 0 and 0, what's it going to be? It's got to be 0. Sine of x over x squared is 0. Okay, all of that to say that this equals, let's, it's a different color, not that, get out. I accidentally chose the text tool. I don't actually know what would happen there. I imagine it opens a text box and then I could type 0. Woo! Why were we doing this whole problem? We were doing this because we wanted the horizontal asymptotes. Y equals 0 is, I'm going to go with N this time, NHA. Let's be inconsistent. There we go. All right, so the coolest part about this problem is that we learned about the squeeze theorem. The squeeze theorem basically says, I'm looking for a good color to like highlight this. Let's go with this, like a soft green, I think. This is the squeeze theorem. Squeeze theorem. Also sometimes called, which I really hate, so don't say this, sometimes it's called the sandwich theorem, right? You got a slice of bread, you got a slice of bread, sandwich. So it's also sometimes called that. I prefer squeeze theorem, like up here, down here, and squeeze it. It's my preference, you know, it's up to you. So we learned the squeeze theorem. If we can trap it between two things that we know the limit of, and those limits are the same, and it's stuck in between them, it must have the same limit. It's like the transitive property, basically. So what I'm going to do is I'm going to stop here. I'll come back in another video, and we'll just keep going. So I've forgotten how to shut this video off. I was trying to do it on my iPad, but I got it. Don't worry. I'll see you soon.